In this video, we're going to do the third problem on this worksheet, exercises on area of planar regions. So the instructions at the top say find the areas of the following planar regions and to sketch each region. So we did the first video, the first question and the second question in previous video, so now we're down to question number 3. And I should say you can always pause these videos and try and work through the question yourself first, actually, before just watching the solution. It's a good kind of exercise, something that you would normally do in class that you might want to try and mimic here while watching the videos, is to do the exercise yourself first and then watch the solution. Check your answers at the end. The worksheets have the answers at the end, and then watch the solution to go through and make sure that you did everything the way you were supposed to do it. So this time we're asked to find the region bounded by y is equal to cos x, y is equal to sine x is equal to 0, and x is equal to pi. So if we just applied the formula, right, we had this formula, integral from a to b of the top of x minus the bottom of x. And if we just sort of took a guess and we said, oh, well, we know what this looks like. The cos starts at 1 and the sine starts at 0. And so this has to be the integral from 0 to pi, because the a and the b are given to us right there, of the cos function minus the sine function dx. And we went about this without sketching or thinking about it a little harder than that. We would be wrong. That is actually not the correct answer to this problem. So let's have a quick look at the sketch and see why that is. So if we go through and sketch the region as we were instructed to do, we are told that we want the cosine and the sine functions from x equals 0 to x equals pi. So if we start with the cosine function, I know it starts at a maximum, goes through the axis at pi over 2, and is at its minimum at x equals pi. So this is a pi over 2 value here. The sine function, I know, has zeros at 0 and at pi, and actually is at its maximum at pi over 2. And so we are looking at the function region that does this. So if we want the areas bounded between y is equal to cos x, sine x, x equals 0, and x equals pi, well, there's a lot going on here. But if we restrict ourselves to those boundary curves, then we are talking about the region that I am shading here in gray. Now, you might notice something. This is a first example here where the curves cross. So we actually have two distinct regions here, and the top function and the bottom function aren't the same in each region. In fact, they flip, right? So the cosine is our top function here, but it's the sine function which is the top function here. And so what we had better do is figure out where they cross, and then we're going to set up two integrals, an integral for the area of region 1, and we're going to add that to the integral for the area of region 2. So let's figure out where these guys cross, and then we'll set up our integrals and evaluate. So we're looking to find where the sine function is equal to the cos function, and you might know the answer to that already from your unit circle. In fact, I kind of hope that you do. But if you don't, how would you go about solving an equation like this? Well, you could divide both sides by the cosine. Sine over cos we know is tangent. Tangent is equal to 1. How do you solve an equation with this? Well, with the arc tangent. And the arc tangent of 1, if you don't know that value, your calculator does, that's pi over 4. So the value that we're looking for here, the intersection value, is pi over 4. So our first region is going to go from 0 to pi over 4, and our second region is going to go from pi over 4 to pi. So let's set up those integrals. The first region is from 0 to pi over 4, we said, and the top function is the cosine, and the bottom function is the sine. So top minus bottom, cos minus sine dx, plus the integral for the second region. So the second region goes from pi over 4 to pi. Now the top function is the sine of x, the bottom function is the cosine of x dx, and we can apply FTC2. So we're going to look for an antiderivative for each of these functions that will be evaluated from 0 to pi over 4. Antiderivative of cosine is the sine. Antiderivative of minus sine is cos, so plus cos. That's nice. And then the antiderivative that we need over here is, well, what do we have? Pi over 4 to pi is what this is going to. So the antiderivative, or an antiderivative of sine is going to be minus cos. And minus antiderivative of cos is sine x. So this minus 1, I'm going to take this minus 1 and I'm going to factor this. Right, these minus 1s, I'm just going to factor them out so that we have everything positive. So we've got sine x plus cos x going from 0 to pi over 4 minus cos x plus sine x from pi over 4 to pi. And you might think, oh, look, it's a negative. These things are going to cancel out. Well, some stuff will and some stuff won't because the bounds are different. So let's run this through. Using FTC2, we're going to evaluate at the top and then the bottom. So sine of pi over 4, cos of pi over 4 minus, open a bracket here, sine of 0 plus cos of 0. And then minus the same thing on this side. So cos of pi plus the sine of pi minus the cos of pi over 4 plus the sine of pi over 4. Cos of pi over 4, sine of pi over 4 are those special values from the unit circle, root 2 over 2. Minus sine of 0 is 0. Cos of 0 is 1. Minus on this side, cos of pi is minus 1. Sine of pi is 0. Minus, and over here we have our root 2 over 2 values for both the sine and the cos. 2 times root 2 over 2. Add these guys together, and I'm just getting root 2 minus 1. Minus the values that are going to be in brackets here. So minus 1. The 0 I'm going to let go with here. And I'm going to get, again, minus. Add these guys together. 2 root 2 over 2. That's just going to give me root 2. And then I have to be careful about the negatives here. So root 2 minus 1 minus minus gives me plus. Minus minus again gives me plus. Those minus 1s are going to cancel nicely. And we're going to have 2 root 2 square units. So something to point out here, in a situation where we had to split the region into 2 because the top and the bottom function changed, you can still give the formula as a single integral if you want to by using an absolute value. So that's the little note that's here, is that very often the area of a planar region bounded by f and g from x equals a to x equals b is given like this. It's given with an absolute value sign so that you don't, if you're typing this into a computer system or whatever, you don't have to know which one is on top and which is on bottom. You can type in the absolute value and that will give you the correct answer. But in practice, how do you figure that out? Well, a sketch is really the best way to figure out where the functions switch, if they switch at all, where a function f is on top and where g is on top.